Hello, welcome back to Maths Olympians or Maths Contest Society. Not very sure what I'm going to end up calling this, but yeah, we're looking at something quite interesting today. So in one of my previous videos, I might have talked about writing a paper regarding the maths behind the multiverse of music that I'll be presenting at the conference in the Royal College of Music in London sometime this summer. Well, one of the most interesting parts during my research was actually something I saw when I was researching a different topic for my Collatz Conjecture paper. As part of my Collatz Conjecture paper, I made this program on Desmos. And Desmos, for people who don't know, is basically a graphing calculator. Desmos is basically just a regular graphing calculator. So you basically input a function. This is a quadratic here, y equals ax squared plus bx plus c, and you can add sliders which can change what a, b, and c are. It's basically to visualize graphs. For example, I can add another one, I can add an expression, and I could put y equals 1 over x, and we get the rectangular hyperbola straight on the screen right there, and you can even look at where they intersect. It's a very useful app, and it has great accessibility. And that's probably how we're going to use this in terms of our music paper. What the program does is essentially it runs a ticker. I was on Reddit one day looking over some Desmos movies, and one of the things I saw was to make these movies, the creators often use something called a ticker, and that's basically what I have up here. The ticker function basically just takes a set of rules and applies it again and again and again and again and again, which is essentially what we need for the Collatz conjecture. When I decided to start graphing the Collatz conjecture, I looked through several different templates that I could probably base my graph off. And it was interesting because there were several different types of graphs. For example, this one, it shows the 4-2-1 loop, and it shows how all the numbers converge on it. And it's quite a beautiful representation of the Collatz conjecture without actually going too deep into the number theory. And it has some key concepts such as the sets that we're going to be needing in our graph. Another graph I found which I thought would be most useful for us was not this one, although this one was quite interesting. You have a set of table here, and you have each of the numbers iterating back to 421. No, the most interesting graph I found was probably this one. And basically what this graph does is you select a value and it iterates it using a ticker function, the same kind I said I saw in those movies. And what it does is it shows you a representation of the Collatz conjecture on the x and y axis, giving it in a way such that you can see the whole set of iterations. This might be useful for our program. So I'm going to try and create something very similar to this, and yeah. So we're going to start our own graph, and we're going to save it as something probably Collatz musical graph or something. Anyways, so once we've done that, we're going to create a ticker like the other program, and we're going to give it a variable g, which we will define later. So first thing we need is a slider, and to do that, we basically need to put some random letters in and just add a slider, and we can get rid of that now. So we're going to have to subscript that, and we'll call this slider nSelected, because that's the number we're going to select. And for now, let's make that 0 and 27. So now we can pick anywhere between 0 and 27. That's the first part of our program done. Easy. Now we want to create a folder and another folder. So after we've made our folders, I've basically made two folders, one for numbers, and that's where we're going to program the actual Collatz sequence and the output, and also another folder for visuals, where we will be adding basically all the stuff that we're going to see, the visual representation of the actual coordinate graph. So the first thing we want to do is we want to add a expression to the numbers section. We're just going to do that by dragging and basically dropping inside. And what we want to do is we want to have our input as a variable. So we're going to have to make another slider. We can do that simply the same way we did last time, just adding a slider, getting rid of this expression, and we'll add the same boundaries and steps as our input function. That's our first step. Now, we also want to label this as n. We had n selected, so it probably makes sense to call it n input. And that's going to be our input, and that can be determined from this, and we'll write a program to relate those two. But that's our first step done. So now we're going to need to make 4 different conditions, and we'll call them C, R, G, S. The only reason I chose these letters is because they're basically the initials of my school, Collatz Royal Grammar School, but there's no obvious reason for those letters. And of course, you remember that we're going to use our G as our ticker function. So what we're going to do now is we're going to take C and we're going to define it as, in Desmos they have curly bracket programming. So we're going to have N, and then we're going to have to subscript that as last, and that's going to be our, it's going to be a variable, and last is going to be a variable in this. And what we're going to want to do is we're going to have to set a condition that if n last is greater than 1, or in other words, we don't actually want to graph that, but if if n last is greater than 1, or in other words, if the Collatz sequence hasn't reached the 421 loop yet, then we can use a colon and apply a condition. So an if condition, if n last is bigger than 1, then S, which is our next category, will be inputted into the set. And we want to make a set bracket, so that's square brackets there. And we're going to have that S is going to, actually we don't need that, S dot join, that's for joining a set, n, and we have our variable n next, so we'll use that. Basically what that condition is doing is that it's an if statement, an if clause. If n last hasn't reached the 421 loop, where n last is the last term in our iteration, then basically what we're saying is that S, which is a set of numbers which we'll write next, which we will use for our visual section, we're basically saying that S will basically will add S, as in we'll add V next to the set S. And that's our second step done. So next we have to define R. Now our second variable R, we're going to have to define it as actually our translation of our n selected onto our n input. So that's whatever we put in here. So basically, when you open up the program, you want to be able to run it like we ran the other program. So we have a slider here which we can select any number, and it should be able to run something visual on here. We don't really want to see this messy stuff here. So what we're going to do is we're going to have a program that will translate this number, whatever we pick, into our n input, so that we can use n input for our term, which we'll put in, I think, later on to define n next and n last. So for R, we're going to have to write a condition saying that n input, subscript input, will tend to, on the subscripts tend to, n input will tend to, and it's not really tend to, that's just a sign, selected, that's our number up here, the slider here, and we're going to have to put a and our and will be that S will be added to n selected. So basically S is just a set of numbers, and what we're doing in this step is we're saying that whatever we select, that's what we're going to start off with in our set S, and we're going to work our way to the 421 loop. So all this condition is saying is that we actually just put n selected in our S set. Okay, so that's been defined. Now, the whole point of the G term is because we really want the C and R and S and basically everything else in our numbers section to be run repeatedly. And the way we're going to do that is basically by having C and R defined in G, because we're going to be running G every 0 milliseconds. So basically it's going to be infinitely running G until we meet a certain condition. And in this case, that's when we reach the 4-2-1 loop. So after finishing our third variable, it's time to define our ticker variable, and that's G. So what we want to do is, like I said, is basically we need to include everything we've done so far. And so we're going to need to talk about n selected, which is basically our input variable, and how that basically equals an input. And we're also going to have to put that when they're equal, basically what this does, we apply C and R. And basically what that's doing is it's just going to, because we have this condition here in C that n last has to be bigger than 1. So as long as that condition hasn't met, as in the Collatz sequence hasn't reached 1 yet, we'll continue applying these two via the ticker. So that's basically the point of the section G, and that's actually the key element in this entire process is probably G and S, because G is going to be running the ticker and S is going to be the set which we're going to use to create the graph on this other side. So now it's time to define S, and S is just a set. So all we're going to have to do now is put S as square brackets, and that's going to be a set. So there's nothing actually that we need to do in that bit anymore. So we can start defining our next two terms, and that are the two actual variables we haven't properly defined. And the first one is n last. N last is just the same as, we can write that as S, where S is our set, and it's going to be multiplied. It's going to be S bracket square bracket S length. Now this introduces a new variable. Later on we'll have a variable L for length, but in this instance it's just saying the length of the set, and it's basically taking the last number in the set. So when we start running the conjecture, or whatever, when we start running the program, we're going to get all the terms that are reached in the program in this set here in S, and so the last thing in the length of S will be the same number as n last. So that's how we define n last. And that was pretty simple in terms of defining that. Now we have to define n next, and this is where we actually apply the rules of the sequence. Now the rules of the Collatz sequence, as we mentioned before, state that if a number is even, we divide by 2, and if it's odd, we multiply by 3 and add 1. So to do that, we need to first write a program that will basically determine if a number is odd or even, and the best way to do that is probably with modular arithmetic. So we're going to have our variable n last, and we're going to say that n last 2, and basically what we're going to do now is we're going to say that if n mod last 2 equals 0, as in if n mod n last comma 2 equals 0, basically means that if it's possible to divide n last 2 by n last by 2 and get 0, as in if it's even, then we basically have to apply using colon. We put the if statement, n last over 2, and that's basically dividing it by 2. So that's the most simple one there is. Otherwise, which is the comma, we put 3n and then last, which is our variable, plus 1, and that's our 3n plus 1. Cool. So now we have defined the Collatz sequence in terms of n next and n last, And we have pretty much finished our numbers section, and that is probably one of the most important sections there is. So now that we've defined n next and n last, all we have to do is now finish by closing these oops, I almost deleted that. We have to finish by closing this bracket here. Yeah, and basically now we can start doing the visuals. Just before we start the visuals, though, I think we should go over what we've done so far. So we have a slider, and that's what we're going to use to input a number. And as you can see, with our new function R, we can actually translate what we put in n selected into our n input, and that's working well, so that's good. Our ticker also seems to be working because it's only through the ticker that we're actually able to run these other programs. So if n selected is 5, we can see that in our S set we have 5, 16, 8, 4, 2, 1. That's because of C, we have the condition that if n last, so in this case, n last, the first n last will be 5. If that's bigger than 1, which it is, we'll have the condition that basically the arrow is an action. So what this clause here is basically saying is that the next number in the iteration will join the set, that is this set here. So after 5, the next number is 16, so they'll just add that to the set, and so on and so on. We've also defined n last as the length of this set here, and n last for this term here would be 5, because 5 is our last term and 16 is the next one, and so on until we get to the 40 sequence. So that's good, because now we can use this set to create our visuals, and of course we have our rules here. So we're going to start the visuals now. So we'll start the visuals by doing what we did last time, and basically adding a expression into the visual section. We want to have it represented on a graph that will look and show something that's basically useful to us. So what we want to do is we first want to get rid of all these axes because we don't really need them. So we can get rid of the grid, we can get rid of the axes numbers, we can get rid of the x-axis and the y-axis. There we go. So now we have nothing on there. In fact, I'm going to change it to reverse contrast because I think it looks better, personally speaking. What we're going to do now is we're going to have the line y equals 0, and we're going to have the range of that line as between, I think a good range would be 0 and I think 1 maybe, yes. So we'll zoom up on this one area here. What we're going to do is we're going to probably, I'm not sure what color we should use for this. We can think about the color later. Anyways, I think next what we had was our x line. So that's x equals 0. And we're going to have a similar sort of range, and that's going to be 0. This time instead of x, so it's going to be y, 0x, y1. So now we have a really nice square sort of thing, and we'll make that white, I think. Just change the color, make this one orange. That's nice. So now that we have this set up here, we have an x-axis and a y-axis. We're going to have to write the condition for the L, the length we were talking about earlier, and that's going to be very, very important in terms of setting up our graph. So what we want to do is we want to write that L equals, and then we need to refer back to the S set that we had, and we're going to have 0, and then we need to do a ellipse, and then a reference back to the length that we talked about in the previous, and subtract 1. The reason we're subtracting 1 in this particular instance, we don't need a capital L. The reason we're subtracting 1 is because we don't actually want to include the number 1 term, or the, so basically in the numbers section here, in the actual set, we don't want the number 1 term. So we can just erase that by getting rid of 1. And that's just defining the term L. So that's fine. We're only going to use that for one really important thing. So now we're going to define x max. And this is basically what they did in the other program. They found the max value and the minimum value. And to do that, I think all we're going to have to do is we're going to have to write a few more definitions like we did with our n last and n first. So it's going to just use a regular max condition, and we're going to say that it's 40, and then s, which is going to be s length. The reason we have 40 here is simply because that's where we're going to position it on the screen, and s length is the same thing we were referring to back here when we look at n last. Yeah, so that's done. Now we need to have a condition for the line, because we want a line basically to show a graph of what the Collatz conjecture will look like. And so to do that, we want to basically draw a curve, and we're going to define the curve as a set of coordinates based on two variables we already have. That'll be L over x max. That's capital X, I think, yeah. And our second point, obviously, will be S over S max. And what that gives us is a set of points. That's not useful on its own. We can also change those points to crosses, make it orange, make it basically look nice. And we can also join these points together by adding lines. And that's really an important thing here. We can also make it dashed, or give it a unique look. Now that we've done that, we want to basically display the maximum number reached and the iterations as well. So to do that, we're going to use basically what we defined earlier as S max, so the biggest number in our set. And we're going to have 0, because that's going to be the point that we don't really care about. We don't really care about the x-axis point. We're looking at the y-axis, which is basically anything on this line here. So what we're going to do for that is we're going to have S, and the set 1. That's a set. We're going to have that whole thing divided by S dot max. So S dot max is basically the largest number in the set S. So that's going to be, for example, 16, and that'll be the maximum number. In this case, that's over here. So yeah, that's very convenient. But yeah, basically, if we change that to 30 or 20, it just decides how much it gets stretched. I just picked 40 because it's a random number. But that's just the x-axis value. It doesn't really have much of an input, although possibly changing it to 20 might make things a little more resolved. I think I'm going to keep it at 40 though, just for the convenience, I guess. We'll make this point here white, so it contrasts with the graph here, and we're also going to want to label that. So you can actually have these things called labels, and we're simply going to label that as need $, and we're going to label that as N selected. That was pretty simple, but we want a capital N, and we need speech marks around this to make it. I don't think that worked. I think we need it around this as well. No, it still hasn't worked. Oh, it's because we used rounded brackets. We need these, not square brackets, curly brackets. I think that should work because curly brackets often. Yeah, and it worked. I don't think we actually need those then. But that's basically what we have now. We have the point that we start on basically labeled, and that's going to be important. So finally, on this side of visuals, we're going to have another important thing, and that's steps, because the other graph looked at the number of iterations that it took for us to reach the final value, and we wanted to kind of do the same thing here as well. So we're going to do steps, and we're going to subscript the rest of the letters, because otherwise we're going to have to make sliders for each of them, and we're going to have that simply equal S length, because, well, like I've said already, S length just describes the number of characters or elements inside S, and we can already see that that's 6 here. and we want to display that as well, so we can do that on the next page. So basically what we're going to do now, just to finish off real quickly, is to position these on the graph, because we have the definition for S steps and S max, but there's actually no sign of it at all anywhere. So what we're going to do is we're going to add a point on the graph, and that's going to be at 0.5. I think this is just eyeballing where it would look nice on this particular graph. Maybe that's a bit too low. Maybe 0.7. Yeah, that's about right. And we're going to label it. We're going to label it number of iterations. And we're going to that as dollar. Forgot where the dollar's gone. And we're going to use the same thing we did last time. Curly brackets. Let's say steps this time instead of the max. Steps. And then we're going to have to do something similar for our max value, I suppose. And that seems to work, but we'll try and put a colon here instead of a semicolon. Also, this feels too large, so let's just zoom up on this, and doesn't feel centered, so I'm going to make that maybe 0.4 instead, or 0.2. That looks better. 0.3. So we're going to also have our number max, and we're going to define that as the max. It's the thing I love about Desmos is that while it's not a programming language, it's so simple to understand, and it's just not time consuming at all. For example, if I wanted the maximum in a set, all I had to do is put s.max, and that gave me what I needed instantly. We're going to try and do the same sort of positioning, probably 0.3, but I'll put it exactly on the x-axis. We also want to have, I think now that it's moved, 0.5 might be better. So we'll just move that back to 0.5. Or maybe, yeah, this to 0.4 as well. We'll make this one a bit lower, so we'll call this 0.13. Yeah, and we'll label it 2. We'll call this one highest number reached, and we'll have a colon, and then we'll define it as dollar and curly brackets, and inside our curly brackets we're going to have what we just wrote about the S max. Again, it's all very, I don't know how to explain it, it's quite simple, and it's very satisfying because you don't have to do much and you still manage to yield a lot from this, because this is now going to help me with writing both papers, the Collatz and the other paper. So we don't actually need S, we need max. Now we have both of those, we can just format it a little bit better because I don't really like how that looks. So we'll make that 0.5, and that's 0.4 still. It's not really centered. We'll make that 0.4, and I don't like the color, we'll make those white. These are all formatting stuff, they're not really that important. That really depends, to be honest. Some people like formatting more than the actual thing. And I don't think we need a point, we can just leave it like it is. There we go. Yeah, that looks much nicer. I think now we can put it in 0.5, and that'll center it. Yeah, so nice. We have our visuals done as well, which is great, because now we can actually start using the program we spent so long writing. Now, before I finish the visual section and start looking at the actual thing, I want to just summarize what we did in visuals. So we had the line y equals 0, that's the white line back down here, and the white line x equals 0, with their respective ranges and domains, which make it look like a really nice graph here. We also have L, which is basically the length of our set that we defined in the numbers section. And basically what we're doing there is we're putting L over x max. What we're saying is that that's the x coordinate, and we're basically stretching out the length of the set, as in the number of things we have, over this line. For example, if I pick, I don't know, 20 or 27, it's going to take all the numbers that we have, and that's going to conveniently fit it on this line here, so that it doesn't, like, I don't know, exceed beyond this line. That's the whole point of that condition there. And the same thing for S and S max. All it does is it makes sure that the largest number in the set S max, basically it just stays inside the boundary. So this number here, it doesn't go any further. It basically scales everything down so it fits on the same thing. So this has 112 iterations, but it fits on the graph of the same size as something which only has 21 iterations. And obviously you could have a million iterations and the same thing would apply. But I don't think we're going to reach numbers that high in this program. Anyways, so that's what those things define. X max is our term for basically the length of our set, and then the coordinate that we have here doesn't actually do anything. It just basically stretches the graph. So if we had it 20, it'd be much further apart. If we had it 0, it'd be like that. 40, it'd be like this. I think we should just keep it at 20 maybe, because that looks much nicer than, I don't know, 40. Definitely much nicer than that. So we'll keep it at 20. I think even maybe 10 or 0 would be fine. So that bit's done now, and we've basically finished the visual section. We have our steps and our maximums basically identified, labeled, and placed on our graph as well, so that's all good. Just a quick thank you to Reddit user 1rpandita, whose ticker function and some of the elements of our visuals and numbers section we took great inspiration from, and without whom this would not have been a possibility. Still unknown, no clue who 1rpandita is. So if you are watching this video, which I highly doubt you are, please leave a comment and tell me who you are, because it has been a pleasure to work with you indirectly. So that's basically the tutorial on how to make something like this. Obviously, a lot of this was inspired by the other graphs I've seen on Desmos, and it's incredible because Desmos can be used to create anything, like movies. I mean literal movies, like an hour-long movie was created on Desmos, a fully animated movie, and it's incredible how maths is so involved in such strange things, and that's why I'm really looking forward to applying Desmos to my music paper, as well as its continued appliances in the Collatz paper that I've been writing. So in the future videos, I will look at how this particular program that I've written just now can be used with mathematics, because on Desmos there's something really cool, and that's basically something that lets you, it's an accessibility feature. If you click on the graph like this, the graph you want to highlight, and then you click Alt-T and H, the graph does something cool. You can actually hear it as notes. This is for people who are visually impaired and can't see, but we can use it to our advantage because it really represents the sound in a nice way, and I think if we can convert it to notes, maybe we can spot a pattern there. I think the beautiful thing about problem solving in maths is that regardless of what it is you're doing, in this case we're looking at the Collatz conjecture, there will always be a connection to something so much larger. And the fact that we were able to write this program and find a connection to something as beautiful as music is just, it's just incredible. And that's what I find so amazing about this. So we don't have much time on this particular video to explore this program enough. So in future videos, I'll be looking at the sound features that are related to the music paper, and also using this program to help me map out the Collatz conjecture. I'm sure this video is already 35 minutes long, so if you've stuck along this long, thank you, and you're obviously very interested and a keen mathematician. So I'll actually end the video there. Please check out all the other videos, like and subscribe so we can grow this channel. My aim at the end of the day is to reach as many people as possible, especially in countries around the world where problem solving is not a commodity that they have access to. Because I've seen the stories in those worlds, and I know how hard it is there to get access to stuff like this. And in countries like the UK, where I come from, we take stuff like this for granted. And for something so beautiful, I think it's something that everyone in the world should be able to access. But that's enough for this video. Thanks again.
Istanbul was Constantinople, now it's Istanbul, not Constantinople. Been a long time gone, Constantinople, now it's Turkish delight on a moonlit night. Every gal in Constantinople lives in Istanbul, not Constantinople. So if you've a date in Constantinople, she'll be waiting in Istanbul.